Donc, il s'agit de M. Guillaume Morissette du CIDCO. J'ai reçu sa présentation en anglais, donc je vais le faire en anglais. Guillaume studied mathematics at the University of Montreal and software engineering at the University of Quebec in Montreal. He has over 15 years of experience developing and managing the development of operations, research software solutions for the medical, logistics, manufacturing, retail, and scientific sectors. His research interests include artificial intelligence, machine learning, embedded systems, and cybersecurity. La présentation, donc, aujourd'hui, an open source framework for autonomous hydrographic surveying platforms. Alors, Guillaume, à toi.
Parfait, je vais partager mon écran ici. Tout le monde voit comme il faut. So, thank you for the introduction. Basically, today we're going to present the results of a few projects that we've undergone with our partners, namely Seafloor Systems and M2 Oceans, which are hydrographic survey equipment manufacturers. So basically, we're going to be talking about an open source framework for autonomous hydrographic survey platforms. In terms of context, the trend towards autonomous systems as automation tools and a force multiplier is well established. In order to avoid silos and redundant engineering, open systems can be designed to establish a baseline for system building. Here, our challenge is basically to design a common core platform for hydrographic survey devices. So depending on the task, there's a multitude of platforms available on the market. Sadly, a lot of the manufacturers each have their own systems. And either they're not interoperable or they use their own proprietary systems. So in order to facilitate the exchange of data between systems, we were tasked to create a common core for such applications. Our design objectives are simple. Basically, we wanted to lower cost by leveraging the current open source and infrastructures, basically both in terms of hardware and software. Second of all, we wanted to allow flexible scaling of the architecture. Everybody has their own sensor set. Each application needs a different set of sensors. So we want to make things as flexible as possible and allow the user to build their own configuration without having to re-engineer the entire system. Third design objective is that we want to allow non-programmers to expand the functionality and basically be able to build their own data processing modules with very simple languages such as Python, which is a widely distributed language. Finally, we want to allow designers to expand the user interface without having to touch the internals of the system. So first of all, the hardware. Well, we can inherit from open source hardware projects all over the world, one of the largest one being the Raspberry Pi computer. So by using that as a central data logger, we basically have a fully fledged Linux system for under $50, which has both networking, USB, UART, SPI, I2C, and HDMI, to name just a few possible electrical interface. So it's readily able to interface a wide area of sensors. It's a very well-known system. It's widely available, and it's becoming one of the staples for a lot of hobby and professional embedded systems. Finally, since it's an open source project, it's stewarded by a nonprofit organization, which means that there's no possibility of vendor lock-in, and their mission is basically to produce the world's cheapest computer. For those of you who are not aware of the Raspberry Pi project, it's a multilateral effort to actually create a computer under $50 that can be used to democratize computer engineering and literacy all over the world. Objectives 2 and 3, basically we can leverage open source infrastructures such as ROS. Rust is what they call the robot operating system. It runs on open source Linux. It's one of the world-leading open source platforms for robotics, with tens of thousands of drivers ranging from basic sensors to complex navigation systems. It can be used for small things such as hobby robots, but it can scale up to large multi-million-dollar industrial robots. It allows people to write their own modules using a large variety of languages such as C++, Python, or even JavaScript and Lisp for more esoteric applications. So this means that we can have a common core written in C++ by experts and allow people to build their own plugins through Python and other languages where performance is less critical. Of course, leveraging an entire ecosystem allows for a world of possibilities. We can readily include a lot of bleeding edge research into our robotics platform. This is not only in terms of sensors, such as you can see on the left here. Most commercial LiDARs already have ROS drivers, but it also includes very complex systems such as SLAM, which is simultaneous location and mapping, and many more technologies such as the real-time simulator that you can see here on the right. So since we were more on the engineering side, we kind of suck at the marketing aspect of things. So we're looking for a better name, but the code name that we found was Poseidon, which is a way to describe the fact that this will basically allow us to unify all our different platforms. What every hydrographic survey platform has in common is the fact that it has a high precision GNSS, it has an inertial measurement unit, and it has an eco sounder. So we can build a framework around the fact that these three devices will always be found. Which brand or make will vary, but we can at least build the top layers of the system to assume that there will be underlying drivers, as you'll see in a moment. So using this fact, we can basically write a system where users will be able to define their own sensor set inside a configuration file, and the top layers will be completely agnostic to the fact of which sensor is where, and just basically receive eco sounder, IMU, and GNSS data. So since we want to write a platform that's going to be portable across platforms, we decided to aim for three very, very different platforms. The first one is the Hydroball 2.0, which is the next generation of the Hydroball 1.0, obviously, which is a towed, self-contained, and pre-calibrated system to conduct IHO-grade hydrographic surveys by non-hydrographers. So basically, the idea here is that it's a fully passive system. You just basically tie it to your boat, drag it around, and you have an IHO-grade hydrographic data to post-process. So that's the first platform. The second platform is the Seafloor EchoBoat 160, which is an autonomous system driven through Mavlink. It's a hydrographic survey powerhouse. It can support multi-beam eco sounders, LiDARs, and pretty much any kind of equipment on the market. So this is one of our higher-end AUVs here at CIDCO. Third of all, the Catarot TS03, which is basically a small remote control catamaran fitted with hydrographic survey tools, which kind of acts as the middle grade ASV for the purpose of this project. The hardware architecture, I won't bore you with the details, but basically you just plug into your regular 12 volt battery. So any kind of marine battery will do. So basically it has its own internal power regulators and sensor arrays. Basically, you flick in the power, and it's going to give you a Wi-Fi access point to which you can connect and access the interface. The software architecture, won't bore you with the details here later, but feel free to ask any question either in the chat or in private. It's basically a three-tier architecture. As I mentioned earlier, we have what we call the sensor pool, which is basically all the different device drivers that are supported by the system. We can always add more if there's a specific sensor. Anybody can add the driver for it. So the idea here is that using the configuration file, you can just define which sensors are into your system, and basically the rest of the platform will just be ready to go. The sensor pool basically provides 3 interfaces to the middle layer, which is a real-time processing layer. Basically, it features and broadcasts depth data, IMU data, and GNSS fixed data. So all the upper layers are completely agnostic to the exact nature of the drivers underneath. So you can basically reuse the same code for different drivers. Here for each different sensor, we had two possibilities just to showcase, to make a proof of concept of the architecture. For sonars, we have the generic NMEA 0183 sonar, but we also have the ImagineX 852, which has its own binary protocol. For IMU, we use the Inertial Sense and Micro INS and the Bosch B&O 055 IMU. And for the GNSS, we had, of course, the generic NMEA GNSS and the U-Blox F9P. So all these devices basically push their data through communication channels known as topics in the ROS languages to the middle processing layer. The middle processing layer basically has a few components, the main of which is the state controller, which provides the state estimates at each and every increment in time. It also receives data from the vitals, basically, which are the system variables such as the temperature and everything that can alter the state, or at least change the state model and its dynamics. The state controller basically pushes its data to 3 different data outlets, which are the telemetry WebSocket, the file management WebSocket, and the system configuration WebSocket. The idea here is to have WebSockets, obviously, which is an open standard defined by RFC 6455. And so it's an open standard. You can easily interface with it through very simple languages. Most importantly, you can interface with it through web design languages. So it doesn't require, at this point, it doesn't require any engineers. You can basically give the task to your nephew who once sold the kitten on eBay to basically do any kind of interfacing job you want with the system. The top layer is the presentation layer. It's just basically a static website. The idea here is that all of the code, all the user interface code is run on the user's devices. So it runs inside either a laptop's browser, your mobile phone, your tablet, but it does not put any load on the actual system. So this allows you to basically run any task that you want without overloading the computer. So this is this was one of the key design points in order to provide a scalable architecture. Here's a couple of screenshots. I sadly didn't have time to grab videos of it, but you can see it's a very simple interface. Each of the sensors go to green if there's any, if everything's okay, they will flick to the red if there's any errors. You have it's a single push button operation to start recording in the upper right corner. You have your heading in pitch roll in real time, your depth line in real time as well. So everything is made very easy to use. Actually, a lot of effort was made to make this as simple as possible. Here you can see the system status. It's always updated in real time. If there's any problems, it will get flagged right away. Getting the data from the device is just as easy as going to the download data section and just basically clicking on the files that you want. Here we have a single recording that's been done. You have the GNSS, IMU, and sonar files, and also the UBX raw GNSS files if you want to do GNSS post-processing. The idea here is that all the data is either available through open formats such as the CSV files here for GNSS, IMU, and sonar data, but also if there's anything proprietary, such as when a lot of GPS models have their own proprietary format, we can extract that as well, and you can just basically put them into the manufacturer's tools if that's what the manufacturer wants. Obviously, we want to shoot for an open system, but we can't convince every manufacturer on Earth to actually follow our guidelines. So we can do both. We've conducted a few field tests. We were lucky enough, due to COVID, things have been made a lot harder, but we've managed to at least get 3 big outings. We went a couple of times to the Rimouski Marina, Depot Lake, and the CHS reference surface. At the Rimouski Marina, it was a very nice location to conduct a quick afternoon test, 1 hour in, 1 hour in and out, really. The pros is that it's very calm water. It's all sheltered, so there's no big waves. It's a flat bottom, so there's a small slope that can at least show you that you're actually getting your data straight. But the cons is that it's calm water and a flat bottom, so it's not really representative of the different difficulties that you might encounter in the field. So it's nice to prove that, to showcase that things are going well, but it's not ideal for showcasing that everything's going fine. The Depot Lake, and I want to just maybe have a small moment of silence for everyone on my team who had to walk into the water here. It's about 4 degrees Celsius, so it's a lot colder than it appears. It'll get worse, but I think that it's worth a mention that you have a great team when they're willing to actually get balls deep into icy water with you. So field test number 2, Depot Lake. It was an incredibly cold day. You see there that we have a little bit of snow. It was an opportunity. We were supposed to be doing a survey on the lake on the next lake over, but sadly it froze over. So when we arrived there was a nice thick sheet of ice on the lake that we had planned the survey for. So it was kind of a baptism by fire. We didn't have any maps for it, so basically we just went and did an RC survey there. So as you can see on the right, it's not the most organized survey, but we managed to grab at least a decent amount of cross lanes where we had a very nice performance. The cons of this survey is that there's not a lot of attitude movement, the greatest of which is mostly the pitch when we step on the gas on the ASV. There's basically there's a little tilt, but as far as the rest, it was very calm water, so the attitude is not a very big factor here, as we'll discuss a little bit later. Also a big con is the battery life. Obviously in the cold, battery life is always a concern. We could almost see, especially for the remote control, that the battery was losing charge at a very alarming rate. So that wasn't that great. And finally, as you can see from the orange shirts, it's hunting season, so we kind of had to go splushing in the water while people were hunting for moose. So it's not that great of a deal here. But hopefully we managed to get some great data, and it allowed us to make a very good proof of concept that we can generalize the system to better scenarios. Finally, field test number 3. It's the pros that it was an agitated sea. It was made on the CHS reference surface, so it's basically reference data. It's great for calibration. The con side is that at the point where we were in the project, it was rushed. We were in the middle of 2 iterations. So we're still processing the data. We're having a little bit of trouble to match and explain every errors. So I wouldn't say it's that great at the moment, but hopefully it allowed us to make a clear. It did make a couple of issues clear, especially in terms of latency compensation, since when we try to lower the costs to very low cost sensors, it can generate a couple of problems. You usually get what you pay for. So if you want to use cheap sensors, you've got to compensate in a couple of ways. So that's that field outing has made that very clear. So lessons learned, really. Building this platform has allowed us to make a few very good findings. First of all, it did allow us to lower the costs significantly for many sensors. Sadly, not all of them. Low-cost sensors are nice, but we need to manage expectations accordingly. Second of all, well, open source is free, but it requires your time, and time is money. So it's great to leverage the collaborative nature of open source by partnering up and actually profiting from other people's mistakes. Because otherwise, if you're all working on your own, everybody makes the same mistakes, and basically there's a lot of inefficiency in that process. So pool your resources together and build a common core, and you can specialize on your own application and capitalize that way. Timestamping data at the source really avoids latency compensation issues. That's one of the big issues that we faced. Basically, when you're using low-cost sensors, they're not timestamped at the source, so you kind of have to make an estimate of the latency in between the different sensors, and that can be quite problematic at times. So cheap sensors yield cheap data. But you can post-process them in a way that they can actually give you some very interesting outcomes. Finally, an open system means limitless application. Now that we have a baseline system, it can actually be turned into a lot of things. So we can use that to conduct specialized surveys. We already have a couple of projects in the pipeline to leverage this platform into different applications, either for collaborative bathymetry, for specialized surveys. So there's a lot of promising avenues for an open source system, and hopefully we've discovered many partners in the meantime during this project that share this philosophy, and hopefully this makes the whole endeavor a lot easier and more effective for everybody. So thank you. You can follow us on GitHub at github.com/CIDCOdev. If you have any questions, don't hesitate to drop them in the chat or drop us a line at CIDCO. Thank you very much.
Merci beaucoup, Guillaume. Très intéressant.